What's going on, everybody? Mr. Diamond here for a potential energy example problem video. Sorry, had to just drop my pen, so I had to go pick it up. We're going to be doing 3 problems related to potential energy, one about gravitational potential energy, and 2 of them related to springs, although the second one is not exactly related to it, but we'll get there when we get to it. So first question said a 25 kilogram boulder is being suspended 10 meters above some sort of treasure. Again, this is some Indiana Jones style protective tomb thing going on. And we want to know, what is the potential energy due to gravity of that boulder? So we know that potential energy of gravity is equal to, well, we care about the force that's being exerted, and the only force that's kind of affecting it while it's in place is gravity. Gravity is equal to m times g, the mass times gravity, and then we care about its displacement, how far it is above a given point, and in this case it is 10 meters, and that would be our height. So m times g times h. Now notice that h is really a relative term. We get to define where the 0 point is on this. 10 meters above the treasure, well, in this case the treasure is the 0, 10 meters above that treasure is the 10 meter mark. Potential energy, you have to define what the beginning point is. If you just say, oh yeah, it's like on the ground, or it's on the floor, or it's up on the shelf, that's not telling you what its potential energy is. At that moment it could be 0 if the shelf was considered your starting point. If you're doing it relative to the earth or sea level or the core of the planet or whatever else, your potential energy is going to be different. So in this case, the potential energy, if it's 10 meters above the treasure, is, we're going to call 0 our starting point, 10 meters the point that it's going to fall, because if it falls, if it were to fall down on top of something, we got enough space here. We can draw a little pedestal here and get a little we'll say it's a crystal. We'll do a crystal-y thing, so it's a little, we'll say it's 10 meters. In this case, our little crystal, or we'll call it a ruby. I've got a red pen right here. So our treasure that is suspended right here, it's going to fall 10 meters. So at this moment, it has the potential to drop a total of 10 meters. So the mass of it is 25. So 25 kilograms. Our gravity in this case is 9.8 meters per second. And then our height is going to be 10 meters. And if we plug all of that into our calculators, second squared, I apologize. It is relevant for the second part that I'm going to get to. It's 25 times 9.8 times 10, we get 2450. If we look at our unit just to double check, we would have kilograms times meters over second squared, which is the same thing as kilograms meters squared second squared, which is the same thing as joules, which tells us that potential energy is also energy. It's giving you the same type of output as a kinetic energy or as a work equation is. But our answer is 2450. Okay, for number 2 and number 3, when you're involving springs, you have to be careful. There is one specific thing you have to watch out for that we haven't really had to worry about in any of our other problems, but because we have a new equation for the force of springs, which was Hooke's law, so F spring is equal to Kx. And then we also have the work of a spring, which is 1/2 Kx squared. We have to make
T-minus 2 hours and counting. Go Team Schwinn.
I don't know if you guys heard the Team Schwinn announcement that was just interrupting my notes, but I will say yet again, I am Team Craft this year. Go Team Craft. But we have two separate equations. We have force of a spring and we have work for a spring. And we have to remember that those are different. And the question that it asks in the notes for the example problem, let me pull it up in front of me really quick just so I can make sure I read it exactly as what it says. It says how much force is needed to compress a spring with a constant of 60 newtons per meter, 5 centimeters from its natural resting position. So because it cares about force, we don't use the work equation we just talked about. We know that force of a spring is equal to the constant, and the constant in this case is 60 newtons per meter, times the distance. And in this case, it says 5 centimeters, but remember, we want it to be in meters. So we're going to have to go ahead and change this. There are 100 centimeters in 1 meter. And we'll plug that in. Or you could obviously just do the move the decimal 2 to the left. That would give you the same answer. So we're going to go ahead and plug in 60 newtons per meter times 0.05 equals 3. It is 3 newtons. And we know it's newtons because this would be centimeters cancel here, meter on top, meter on bottom, because it's caring about force. We know that the force of a spring that has that's only being compressed 5 centimeters is a total of 3 newtons. All right, and then finally, we have what is the spring constant when it takes 5,046 joules to stretch the spring 0.78 meters. Notice that now we have joules. Last time we wanted force, which meant our unit was going to end up in newtons. This time we have joules. That tells us that we have to use the work equation. So work of a spring is equal to 1/2 kx squared. Now we're going to have to rearrange. We want to get k by itself. So k by itself would result in work. I'm not going to do the spring. I'm just going to do s. And we're going to end up multiplying that 2 since we're dividing by 1/2. So it'll be 2 work due to the spring divided by x squared. So we'll get 2 times 5,046 joules over 0.78 meters squared. Go ahead and we'll plug this into our calculator. 5046 times 2 divided by, I'm going to put it in parentheses, 0.78 squared. I get a spring constant that is pretty massive, which is probably unrealistic. Notice I didn't need to convert it because it was already in meters in this case. So we get 16,587.77, or 1/6, and I think we got 2 sig figs there, so we'll just go ahead and call that 17,000. And we know what the unit should be, but if we just double check, a joule is equal to a kilogram meters squared second squared. And if we were to rearrange and solve for these pieces, we would get, we're dividing it by a meters squared. We would get a meters squared will cancel. We'll get kilograms per second squared. I think I might be missing something over here. Oh, newtons divided by meters. A newton divided by a meter. A newton is a kilogram per meters per second squared. If we divide that by a meter, the meters would cancel. You'd be left with kilograms second squared. Okay, took me a second to figure it out. But this is a really weird one, which is why it wasn't kind of immediately obvious what was happening. The answer, or the unit of your work spring, is equal to a newton over a meter. In this case, we would end up with a kilogram over a second squared as the last pieces, which would be the same thing as dividing a meter away from a newton. Again, which is really weird, but we would be ending up with our same unit. We expect newton over meter. All right, those are the example problems for potential energy. Like I said, the real difficult stuff is going to be when we kind of combine all of our energy stuff together, but we won't be doing that really until next week. If you have any questions, please send me an email. Otherwise, this is Mr. Diamond signing off. Have a good rest of your day, everybody.